Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through everything you need to know for the upcoming test on number theory. So we're going to go through powers, square roots and cube roots, factors and multiples, factor trees, and then some challenge questions. So let's start with powers of numbers. So what is a power? You've probably seen an expression like this before. We call this larger written number as the base and the smaller written number here the power or the index. So we read this as 4 to the power of 5. This number is said to be in index form because it's something to the power of something. So what exactly does that mean? Well, we call this number here the base, and that's the number being multiplied. This number tells us how many times we multiply the base by itself. So 4 to the power of 5 means we multiply 4 by itself 5 times. So 4 to the power of 5 is 4 times 4 times 4 times 4 times 4. 4 multiplied by itself 5 times. So this is said to be written in expanded form. Now, if you're asked to evaluate this, this means just tell me what it equals. Give the number. So 4 to the power of 5 is 1,024. So please make sure you understand 4 to the power of 5 does not mean 4 times 5, which is 20. A lot of people make that mistake. It means you multiply the base by itself this many times. So there is a special case of raising to the power. If we raise a number to the power of 2, we call this squaring. So 4 to the power of 2 just means you times 4 by itself twice, and 4 times 4 is equal to 16. So this is called 4 squared. If you square a number, it means you times it by itself. So if we square the number 4, we get 16. If we want to go the other way, we call that square rooting. So squaring and square rooting undo each other in exactly the same way as multiplication and division. If you multiply a number by 3, then divide by 3, you're back where you started. Similarly, if you square a number, which means times it by itself, and then you square root your answer, you're back to where you started. We use this symbol here for square root. So the square root of 16 is equal to 4. So when we're square rooting a number, let's say we're square rooting a number like 25, we're saying which number do you multiply by itself to get 25? So the answer to that is 5, because 5 squared, or 5 times 5, is 25. Now 25 happens to be a perfect square. On the other hand, something like 26 is not a perfect square. The reason 26 is not a perfect square, you can't multiply a whole number by itself to get 26. So the square root of 26 will not be a whole number. 36 is a square number. It's a perfect square because it's 6 times 6. So the square root of 36 is 6. The square root of 36 is saying, what number do you square? What number do you multiply by itself to get 36? So the square root of 26 is going to be more than 5 and less than 6. But it's not going to be a whole number. Perfect squares, when we square root them, we get a whole number. So similar to squaring is cubing. Cubing is when you raise a number to the power of 3. And that means you multiply it by itself 3 times. So 3 to the power of 3, we multiply 3 by itself 3 times. So 3 times 3 is 9, times another 3, and you get 27. So this is said to be index form, expanded form, and this is the answer I'd give if I was asked to evaluate. So when you cube a number or raise it to the power of 3, you're multiplying it by itself 3 times. So when I cube 3, I get 27. Because 3 times by itself 3 times gives 27. So if I want to go the other way, we're cube rooting. Just like squaring and square rooting undo each other, cube and cube root undo each other. So if I asked for the cube root of 27, so that's the same square root symbol but with a little 3 inside. Cube root of 27 is saying what number do you cube? What number do you multiply by itself 3 times to get 27? And we know the answer is 3. If you cube a number and then cube root it, you're back to where you started. All right, let's now have a crash course in factors and multiples. So a number A is a factor of another number B if A goes into B evenly. Here A and B just stand for random whole numbers. Now if A is factor of B, that is equivalent to saying B is a multiple of A. What does all that mean? Well, let's take a number like 12 and look at its factors. So the factors of 12 are the numbers that go into 12 evenly. Each of these numbers, 1, 2, 3, 4, 6, 12, goes into 12 evenly. For example, if you divide 12 by 6, you get a whole number. The answer is 2. So because of that, 6 is a factor of 12. 6 goes evenly into 12. Another way of saying that, if 6 is a factor of 12, it means 12 is a multiple of 6. On the other hand, if I were to divide 12 by 5, I get 2.4 or 2 remainder 2. 5 does not go evenly into 12 because there's a remainder. You can't multiply 5 by a whole number to get 12. So because of that, 5 is not a factor of 12. Note that 5 wasn't on this list. So factors of 12 are the numbers that go evenly into 12. Factors of a number must be less than or equal to that number. Note that all the factors of 12 are 12 or below. You can't have a number higher than 12 being a factor of 12. Multiples, on the other hand, they're larger. So factors of a number are smaller, multiples of a number are larger. So 12 is a multiple of all of these numbers because each of these is a factor of 12. When we're talking about multiples, we're sort of counting up by that number. So multiples of 4 will be 4, 8, 12, 16, 20, 24, and so on. Notice that we're just doing our 4 times tables. We're just going up by 4. Each of these is a multiple of 4 because 4 is a factor of each of these numbers. 4 goes into 4 evenly, 4 goes into 8 evenly, 4 goes into 12 evenly. So when you have a situation like this, a number goes evenly into another number, the smaller number is a factor, the larger number is a multiple. So it turns out every whole number greater than 1 always has at least 2 factors, itself and 1. Just like for 12, notice that itself and 1 are always factors. But for some numbers, these are the only factors. Numbers that have exactly 2 factors are said to be prime. In other words, a number is prime if its only factors are itself and 1. If a number's not prime, that means it has more than 2 factors, then we say that number's composite. And note that 1 is neither prime nor composite because 1 only has 1 factor. So for example, the number 11 is prime. Its only factors are 1 and 11. It only has 2 factors. There are no numbers other than 1 or 11 that go evenly into 11. But 12, the number from before, that's clearly composite. 12 has lots of factors. It has other factors besides itself and 1. In fact, it has 6 factors. Because it has more than 2 factors, it's composite. 13 is another example of a prime number. Its only factors are 1 and itself. 14 is composite. It has factors that are 2 and 7. 2 and 7 go evenly into 14, so 14 has factors besides 14 and 1. That's why it's not prime, it's composite. So note that 2 is the only even prime number. All other even numbers have a factor of 2, so they're not prime. So most of prime numbers are odd, but not all odd numbers are prime. An example is 15. 15 is odd, but it is definitely not prime because it has factors other than itself and 1, namely 3 and 5. 15 actually has 4 factors. 1, 15, 3, and 5. Because it has more than 2 factors, it is composite. All right, let's now use the idea of factors and primes to calculate factor trees. So it turns out any integer greater than 1 can be written uniquely up to order as the product of primes. So to do this, we use a factor tree. Okay, what does that mean? Well, it will become clearer after we do the factor trees, I promise. So this is how you do a factor tree. You start with a number and you keep factorizing it. You just find 2 numbers that multiply to it. And you keep going till all your numbers are prime. So what we're going to do is we're going to find 2 factors of 36. We don't choose 1. We never want 1 to appear in our factor trees. So we can choose any factors. For example, 6 and 6. 6 times 6 equals 36. Now 6 is not a prime number, so now I'm going to factorize 6. I keep going till I've only got prime numbers. So 6 has factors of 2 and 3. 2 times 3 is 6. Now 2 and 3 are prime numbers. I'm going to stop because here I have only prime numbers. So 36 is 2 times 3 times 2 times 3. It doesn't matter the order you multiply things. So it wouldn't matter if I did 2 times 2 times 3 times 3. That's what I meant here about uniquely up to order. When I say that you can write a number uniquely as the product of primes, I'm saying that anytime you start with 36 in the factor tree, you'll always end up with 2 2s and 2 3s. It doesn't matter in which order. It's unique because no other number, when you do its factor tree, will you end up with 2 2s and 2 3s. So 36 is 2 times 2, which is 2 squared, and times 3 times 3, which is 3 squared. 36 is 4 times 9. So I've written 36 as the product of prime numbers. 2 times 2 times 3 times 3. Let's do something similar for 60. So it doesn't matter which factors you choose at the start. It doesn't matter if I go 12 and 5, 10 and 6, 30 and 2, as long as I don't choose 1. So let's choose 10 and 6. 10 times 6 is 60. Make sure when you're doing these factor trees, the two numbers times to the number, not add. Some people make that mistake. So neither 10 nor 6 are prime. So I keep going. I keep factorizing until I only have prime. So 10 is 5 times 2. 6 is 3 times 2. So 60 is 5 times 2 times 3 times 2. It's unique. No other number has a prime factorization that has a 5, a 3, and 2 2s. So 60 as the product of primes, it's 2 times 2, or 2 squared, times 3 times 5. Okay, we can actually use these prime factorizations to calculate highest common factor and lowest common multiple of two numbers. So this is how you do that. You draw this, which is called a Venn diagram. You have two overlapping circles here. One for the first number 36, one for the second number 60. So in this overlapping region, this region is in both circles. You put the primes that appear in both circles. So in both of these factorizations, did we have 2 2s and a 3? So what I'm going to do is put 2 2s and a 3 in the middle. These were common. These were things that both 36 and 60 had in common. Just like if you and I both like soccer, we have that in common. Both of us have that. So we put what is in both factorizations in the middle. So what I need to put over here is anything in the 36 factorization that was not in the 60 factorization. Well, when I factorized 36, I actually had 2 3s. I've only got 1 3 in the middle in the 36 circle at the moment, so I'm going to put another 3 there. As for 60, well, I've already written the 2, 3, and 2 in the middle because they were common. I haven't written the 5, so I need to put the 5 inside the 60 circle. So note, all the numbers in this circle multiply to 60, all the numbers in this circle multiply to 36. So to calculate the highest common factor, you just multiply the numbers in the middle. So the highest common factor of these two numbers is 2 times 2, which is 4, times 3, which is 12. 12 is the highest common factor of 36 and 60. It is the highest number that's a factor of both 36 and 60. The lowest common multiple of 36 and 60, that's obtained by multiplying all of the numbers inside the circle. So 3 times 2 is 6, times 2 is 12, times 3 is 36, times 5 is 180. 180 is the lowest common multiple of 36 and 60. Why is that? It is the lowest number, that's a multiple of 36, but also a multiple of 60. There's no number lower than this that is a multiple of both numbers. All right, let's now look at a few harder questions. So let's try this first challenge question here. The highest common factor of 30 and 8 is 15. A is between 50 and 100. What's the value of A? So here A is just some random number. I'm saying some random number and 30 have a highest common factor of 15. If that random number is between 50 and 100, what is that random number? So note the prime factorization of 30 is 5 times 3 times 2. They are the primes you multiply together to get 30. So 15 is a factor of 30 because 5 times 3 is 15. This must be a factor of 30 because it goes evenly into 30. So if I want to find another number who has a factor of 15, it's also going to have 5 times 3 in its prime factorization. If I want 15 to be the highest common factor of some number A and 30, it has to have 5 times 3 in its prime factorization, but it can't have 2. If it had 2 in its prime factorization, the highest common factor would be 30. So what I need to do is multiply these numbers here by another prime other than 2. So I could multiply it by 3, but 5 times 3 times 3 is 45, and 45 is not between 50 and 100. The highest common factor of 30 and 45 would indeed be 15, but I don't want that number because it's not between 50 and 100 like the question asked. So let's try the next prime number. After 2 and 3, the next prime number is 5. Well, 5 times 3, 15 times 5 is 75. So the highest common factor of 75 and 30 would be 5 times 3. That's what's common to them. These two have a highest common factor of 15. 75 is between 50 and 100, so it must be the case that A equals 75. All right, let's look at this question here. So we're being asked to find two prime numbers whose sum is 18 and product is 65. So sum means plus. We want to find two prime numbers that add to 18 and multiply to 65 because product means times. So let's go through and find pairs of prime numbers that add to 18. Well, we can't choose 1 and 17 because 1's not prime. So the next prime that we're looking at, 2, well, 2 and 16 doesn't work because 16's not prime. How about 3 and 15? Well, 3 is prime, but 15's not. If you keep going like that, you'll see that 5 and 13 are two prime numbers that add to 18. The next prime number after 5 is 7. 7 and 11 are two primes that add to 18. So which of these pairs is the answer? Well, we want them to multiply to 65. 7 times 11 is 77, not 65, so we can exclude that. The numbers are 5 and 13. 5 is prime, 13 is prime. The two numbers add to 18 and multiply to 65. All right, let's look at this last question. A number is the perfect cube of a prime. How many factors would it have? So the simplest way to do this would be to choose any prime number and cube it. So 2 cubed is equal to 8. And remember, 2 is a prime. So 8 is the perfect cube of a prime. So factors of 8 are 1, 2, 4, and 8. It has 4 factors. Well, was that just a fluke? Would it work for another perfect cube of a prime? Well, let's check. Let's cube 3. So the factors of 3 cubed, which is 27, so they will be 1, 3, 9, and 27. Again, you can see that we get 4 factors. So why is this? Well, it turns out there's a pattern. If you have the perfect cube of a prime like this, the factors are 1 and the number, the prime number you cubed, and then the square of that. So here, the prime number we cubed is 3. So the factors are 1, 3, 3 squared, 3 cubed. The same would work for 5 cubed. Now, 5 cubed is a large number. It's 125. But I can tell straight away that it will have 4 factors. The 4 factors will be 1, 5, so the prime number that I cubed, 5 squared, and 5 cubed. So it doesn't matter which prime I cube, the answer to this question is always the same. It is always 4. The perfect cube of a prime number always has exactly 4 factors. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Best of luck for your test and have a great day.